is Chemistry 2, Chapter 10, Gases. There are multiple parts to this chapter. The first thing we need to talk about is characteristic of gases. So you can see in this picture representation, a solid versus a liquid versus a gas. So we're only talking about gases in this chapter. So gases have an indefinite volume and an indefinite shape. What that means is their volume depends on the container they're in, and so does their shape, unlike that of a solid or a liquid. A solid obviously has a specific shape and a specific volume because of how the molecules are held. A liquid has a specific volume, but its shape may be dependent on what container it's in. A gas, however, is going to spread out or contract to fill whatever volume it is in, and therefore the shape can also change. So indefinite volume and an indefinite shape, meaning it truly depends on the container or the holding space of the gas. As you can see from the picture, gaseous particles like to be far apart. They're a great distance apart compared to those of a liquid or a solid. And these particles of gases move very rapidly. There are very weak attractive forces between them, unlike those of a liquid or a solid. So they're spread out apart and they move in a constant, random, rapid motion. So, like I said, the first part is about the kinetic molecular theory, or the KMT. The kinetic molecular theory just helps us to understand behaviors of gas molecules, and later on we'll talk about specifically the ideal gas. So the word kinetic in our case is going to mean motion, and molecular means molecule. So we're talking about molecular movement or motion and the theory behind that. So KMT, the kinetic molecular theory, is motion of molecules, specifically gases. So, based on the idea that we just said, gases are always in a random, rapid motion. This really only applies to an ideal gas, the kinetic molecular theory. So what is an ideal gas? Well, an ideal gas, if something is ideal, it's perfect. Okay, so basically an ideal gas is something that is imaginary. I know, hard to believe. We're talking about something that doesn't really exist, that fits every single assumption of the kinetic molecular theory perfectly. Now, we do have some gases that are almost ideal, and those would be the noble gases. So helium, neon, argon, krypton, and xenon. They do act as ideally as possible. So we like to think of those when we're talking about the kinetic molecular theory. But truly, in all honesty, if we could say what gas fits every assumption perfectly, there isn't one. It's an ideal gas. So assumption number one under the kinetic molecular theory is that gas particles are very far apart from each other. Realistically, that's not always the case given specific situations, but ideally, they're all far apart. Assumption number two is that gas particles collide elastically with each other, and they will also collide elastically with whatever walls are containing them. Now, you have to understand that a wall could be like a beaker, a stoppered flask, or it could just be the ground, the atmosphere, the layers, things like that. So container is a very vague word in our case. So you have to know what is an elastic collision. An elastic collision is a collision in which no net loss of kinetic energy happens. So imagine that you're playing pool and you hit the cue ball. It's moving towards, we'll say, the 8 ball. Hopefully it's your last hit. If this was an ideal elastic collision, the cue ball would transfer all of its energy to the 8 ball, and the 8 ball would continue moving with the same amount of energy. No net loss. Unfortunately, we have some transferring of energy that happens, which we don't think is ideal. So the ideal assumption is they're always elastic. Unfortunately, they're pretty much inelastic. So what happens is, the cue ball does transfer its energy to the 8 ball, but not all the energy is transferred. So think about that. If the cue ball hits the 8 ball, if it was an elastic collision, the cue ball would immediately stop moving and the 8 ball would immediately continue moving with the same force. That's not the case. Usually it'll hit, the cue ball will move a little bit farther, the 8 ball will pick up speed. That's an inelastic collision. Assumption number 3 is that gas particles are in a continuous, rapid, random motion. Continuous meaning they never stop, rapid meaning they're always at the very same fast pace, and random meaning they are randomly moving. So what happens is, it doesn't matter which picture you look at, the one on the left is nice because it has straight lines. What we're saying is that these gas particles should continue in a straight line until they hit with something else and they're deflected. So they may hit into each other or they may hit into the container wall. The key to not being ideal is the word continuous and I would say rapid. Continuous, sometimes they slow down, sometimes they briefly stop before they pick back up. So like I said, we're talking about ideal gases, but unfortunately, that's not realistic. Assumption number 4 is that there are no forces of attraction or repulsion between gas particles. So they are truly hitting off each other in that rapid random motion. There is no attraction and there's no repulsion. Unfortunately, we know because of chemical bonding, there is some forces of attraction or repelling happening. We can't help that. That's just nature. But ideally, we would like to say there is no attraction or repulsion happening. So we like to say that gas particles collide, but they do not stick or bond to each other or attract to each other. Instead, they can continue moving in whichever direction they're propelled. So if you kind of look at the video here, you can see that there's no attraction. These are truly just moving wherever they want. And when one hits off of each other, it's pushed in a different direction. Unfortunately, in an ideal or in an unideal world, in the world we live in, there are some tiny forces of attraction and repulsion, so sometimes that does affect the rapid random motion. So this assumption kind of goes with assumption number 3. And then the last assumption for the kinetic molecular theory is that the average kinetic energy of a gas particle depends on its temperature. So however many gas particles you're talking about, the average kinetic energy, the average speed, motion of that gas particle depends on the temperature. So we would like to think that ideally, low temperatures would cause less kinetic energy because they're slowing down. They're almost turning more to a liquid if you think of it like that. They're slowing down, and when you freeze something or liquefy it, when you're changing states, you have to lower that temperature to get the molecules to slow down to change their state. High temperatures would cause more motion because you're heating it up, you're exciting them more, they're getting more motion, more activity. So we like to say ideally, an increase in temperature is an increase in energy. This is definitely an ideal and can happen in the real world. However, there's limits. Depending on the gas you're talking about, there are low limits to where if you lower the temperature anymore, they don't act as a gas anymore. They act as a liquid, or maybe they sublimate to the opposite. They turn into a solid, or maybe there's a high. So there's only a certain temperature they can hit the highest at. So that is the introduction to chapter 10, and those are the 5 kinetic molecular theory assumptions, specifically talking about an ideal gas. So an ideal gas would have all 5 assumptions to a T. Like I said, unfortunately, the noble gases are the closest ones. They do hit a lot of those, but not perfect.